we are going to start talking about the mathematical relationship between the different variables that can be measured for a gas. So this is called the combined gas law, and the laws that are combined into the combined gas law are Boyles Law, Gay-Lussac's law, Charles's law, and Avogadro's law. We will learn the combined gas law, but also the individuals. All right. We are going to skip this slide for now because we are not in class with a partner. And let's just go ahead and talk about the changes that affect gases and the quantitative properties that can change. So when gases undergo a change of conditions, so maybe you have a balloon or a tire or an inner tube that you might float on in a pool, and there's some sort of change in condition. Maybe the temperature changes. Their quantitative properties are going to change. That means the measured values. So the four measured values that we use to describe the conditions of a gas are the following. Pressure, which remember is the force that the particles are hitting the wall with. The volume of the gas, which is the space that it takes up. The temperature, which is related to the speed of the molecules. And the number of moles, which is related to the number of molecules. So when all four variables are changing, you would use what's called the combined gas law. So key thing here is that we're talking about changes in condition. So if you have changes in condition, you would use a combined gas law, and here it is. Your notes packet, double check it. You might have a typo here where I'm pointing. If you have a 2 right here where I'm pointing, please change it to a 1. Okay, so this is the combined gas law. What you need to make a note of in your packet is that all of these ones here on the left refer to what's called initial conditions. So before the change happened, this is the pressure, the volume, the number of moles, and the temperature before a change happened. Then the change happens. Again, maybe the temperature changed. Maybe you put more air in the tire. Something happened. These are the final conditions. So the final pressure, the final volume, the number of moles in the end, and the final temperature. So please make sure you have a note that the 1s indicate starting conditions and the 2s indicate ending conditions. Little side note here, all temperatures must be in Kelvin. And a reminder, temperatures to convert from Celsius to Kelvin, you add 273 and make a little mental note that there's no degree symbol. We just say Kelvin, not degrees Kelvin. All right. On a little piece of paper, or maybe in the margin of your notes, I want you to write this PV over NP. This is kind of the structure of the combined gas law. What we will do when we're analyzing problems is we will look at what variables are changing and we'll keep them, and we will get rid of the variables that are not changing. So for instance, if pressure remains the same but everything else is changing, you would just drop the P out of the equation. It would just go away. All right, so we're going to talk through the 4 possibilities of 2 pairs. So anytime 2 of the variables are changing, how is everything else going to be affected? So if we have a scenario where only pressure and volume are changing, but temperature remains the same, that is going to be what's called Boyles Law. The mathematical equation for it is P1 times V1 equals P2 times V2. What this really works out to mean is that pressure and volume are inversely related. All right, so with your hands, I want you to do 1 thumbs up and 1 thumbs down. That is an inverse relationship. If pressure goes down, volume goes up, and vice versa. The little GIF over here is representing that. When the weights are added and the volume decreases, the pressure goes up. We can also see that on FET, so let's look at it real quick. All right, so let's put some gas in the container. Put a lot of gas in there. Okay, and let's take a look at what the pressure is. The pressure here is 28-ish ATMs. Okay, so I'm going to smush the gas into a smaller space. The proper scientific word for that would be compress. I'm going to compress the gas. What's happening here to the volume? The volume is going down. What do you predict will happen to the pressure? Well, because it's an inverse relationship, if the volume decreases, the pressure should go up. So watch the pressure. There it is. So the volume decreased, the pressure increased. That is called an inverse relationship, and that is Boyle's law. The second possibility is if pressure and temperature are changing, okay? So pressure's on the top, temperature's on the bottom. The equation, therefore, is pressure P1 over T1 equals P2 over T2. This GIF over here, as the candle is heating the gas sample, notice that the pressure is consistently increasing. That's because the particles move faster and faster and faster. That's going to increase the pressure. Let's take a look again at the FET. And let's just go to the one where we already have a gas. Oops, closed it, y'all. Okay, put some gas in there. All right, so notice that the temperature is 300 Kelvin and the pressure is about 20. All right, I'm going to heat it up and watch what happens to the pressure. So heat increases the speed of the molecules. They're moving faster and faster and faster and faster and faster. What's happening to the pressure is no longer 20. It's like up to 100 now, okay? So with your hands, do 2 thumbs up. That's a direct relationship. As the temperature went up, so did the pressure, both hands. Now put 2 thumbs down, okay? That's showing us the direct relationship if they both decrease. So watch what happens if I cool the gas. Temperature is decreasing, and so is the pressure. That is the direct relationship between pressure and temperature. All right, back at it. Next up, volume and temperature. Volume and temperature have a direct relationship as well. Volume is on top, temperature is on bottom in the combined gas law. So V over T, V1 over T1 equals V2 over T2. The description is the volume and the temperature are directly related. The GIF over here is showing us as the flame gets bigger, the temperature is going up. Do 1 thumbs up. As the temperature goes up, so does the volume. So do another thumbs up. So 2 thumbs up. As the temperature goes up, so does the volume. I'm not sure that we can make that happen here on the FET because I don't think that we can make the volume change. So we're just going to have to use that GIF that we saw there. As the temperature goes up, so does the volume. That's a direct relationship. The final law is called Avogadro's law, and this is if volume and number of moles is changing. This is the most kind of simple relationship to understand because if you have ever seen someone blow up a balloon, you understand it. N stands for the number of moles, and V is volume. So if you increase the number of moles by blowing up a balloon, then it's going to increase in volume. If you let the air out, that would be a decrease in the number of moles. The volume will decrease and it will get smaller. So again, that's a direct relationship. Give me 2 thumbs up. Volume goes up because the number of moles also went up. They both increase. All right, so we're going to practice looking at some word problems, and all we're going to worry about today is picking out what is the right equation to solve it. So a gas has a temperature of 14 degrees Celsius and a volume of 4.5 liters. If the temperature is raised to 29 degrees Celsius and the pressure is not changed, what is the new volume of the gas? So the first thing we want to consider here is what variables are actually changing, okay? So ask yourself, of the variables, pressure, volume, temperature, and number of moles, which ones are actually changing? Well, temperature is changing from 14 to 29, so that's a change. And there's an initial volume of 4.5 and a final volume because it says what is the new volume. So temperature and volume are changing. It says pressure is not changed, so that's not involved. And it doesn't say anything about number of moles, so that's not involved. So all you really need to write down in your notes is what's in this yellow square here. The equation that we would use between volume and temperature is V1 over T1 equals V2 over T2. That is Charles's law. I'm not going to quiz you on the names, but we need to know the formula. Okay, number 2. Let's read it together. A sample of helium gas has a volume of 200 milliliters at 0.960 atmospheres. That's the pressure, remember. What pressure in atmospheres is needed to reduce the volume at constant temperature to 50 milliliters? All right, so ask yourself, of those 4 variables, what's changing? Well, volume is definitely changing from 200 milliliters to 50 milliliters. We had a starting pressure of 0.96 atmospheres, and it asks for the new pressure, so pressure is changing. It says constant temperature, so temperature is not changing, and it doesn't say anything about number of moles, so we need to use the equation that only uses pressure and volume. That is going to be Boyle's Law. It's the equation here in the yellow box. So that's what you want to write down in your notes. Again, I don't care that you know the name, Charles's Law. I do want you to be able to make this equation from the combined gas law. All right, the final question, number 3. A balloon contains 0.15 moles and has a volume of 2.2 liters. What will be the volume when I add an additional 0.2 moles? So ask yourself what's changing. Well, moles is changing. That's the N in the combined gas law because it stands for number of moles. And volume is changing because it started with a volume of 2.2 liters and it says what will be the new volume. So if V and N are changing, we keep those variables, get rid of everything else in the combined gas law, and what's left is what's in this yellow box. V1 over N1 equals V2 over N2. That's what you want to copy down. That's the equation that would be used to solve this word problem. That is called Avogadro's law.
All right, so we are going to run through our examples here, starting with number 1. So we have a gas occupies 100 milliliters. I'm going to do some highlighting. 100 milliliters, that's a volume, at 150 kPa, that's a pressure. Find its volume, so volume, I'm going to go back and highlight that word blue. Find its volume at 200 kPa, that's a pressure. So what is changing here? Well, the two things that are changing are pressure. Oh, hang on, I'm going to color code here. The blue thing that I highlighted was volume. So volume is changing. And then the other thing that's changing, I highlighted in green, is pressure. So we're going to think about our equation, PV over NT. I say peas and veggies go on the new table. Peas and veggies on the new table. And we are only going to keep volume and pressure. So N goes away and T goes away. So we have P1V1 equals P2V2. So that's our equation that we're going to use. This is called Boyle's Law. P1V1 equals P2V2. All right, so what we're going to do is make a list of our variables and fill them in. So P1, V1, P2, V2. Now we're going to go back and carefully read the problem and get the right numbers listed with the right variable. So P1 is our starting pressure. All right, a gas occupies 100 milliliters, that's a volume, at 150 kPa, that's a pressure. So this is my starting pressure, 150 kPa. I also just passed by my starting volume. It was 100 milliliters. So I'm going to fill that in as my V1, 100 milliliters. All right, keep reading. Find its volume. So new volume is a question mark. I'm going to put that there. At 200 kPa, so that's the new pressure. 200 kPa is my new pressure. That's going to be P2. The next step would be to substitute in the numbers. So if we're doing the guess method, we are on the substitute method. So P1 is 150 kPa multiplied by V1, because P1 times V1 is, P1 V1 is P1 times V1. So multiplied by the starting volume of 100 milliliters equals, my final pressure was 200 kPa times my ending volume, I don't know, it's V2. All right, so this is my equation here that I need to solve. You are going to use algebra to solve this. So this equation here, all this stuff, I need to think through algebra. How am I going to get V2 by itself? It's multiplied by 200 kPa, so I need to divide this side by 200 kPa. So divide by 200 kPa, divide by 200 kPa. That cancels. And so I have V2 equals 150 times 100 divided by 200. The units kPa canceled. My ending unit is milliliters. So this is what I'm going to do in my calculator. 150 times 100 divided by 200. Times 150 divided by 200 gives me 75. So my ending volume, V2, equals 75. And again, like I said earlier, the unit left over in the end was milliliters. You see that right here. So milliliters is my unit, 75 milliliters. All right, let's think through what happened here, y'all. What happened to the pressure? The pressure went from 150 to 200, so the pressure increased. What happened to the volume? The volume went from 100 to 75, so the volume decreased. So if I zoom in on this this little segment here, what I see is the volume decreased and the pressure increased. Remember that that is called an inverse relationship. So you can check your answer and make sure that this makes sense. Yes, pressure and volume change in an inverse way. If one goes up, the other goes down. All right, let's move on to number 2. Number 2 says a gas's pressure is 765 torr at 23 degrees Celsius. Now, I like to joke and say that the C in Celsius really stands for cringe. Ugh. 23 degrees Celsius. We are not allowed to use Celsius anymore. I like to just go ahead and change it immediately. So I'm going to go to my calculator and do 23 plus 273 because that's Celsius plus 273, which converts to Kelvin. 296 Kelvin. So 296 Kelvin is the temperature that I will use. 23 will never be seen again. All right, at what temperature will the pressure be 560 torr? Okay, so what is changing here? We've definitely got pressure because we have 2 different torr values, and we have a starting temperature, and it says at what temperature will it be different. So the variables changing here are pressure and temperature. So if we think through peas and veggies on the new table, to make sure we've got the right equation here. Pressure and temperature are changing, so I'm going to keep those. Volume, not mentioned. Number of moles, not mentioned. So I've got P over T. So my equation is going to be P1 over T1 equals P2 over T2. Okay. Next up, I'm going to make a list of my variables, P1, T1, P2, T2. And I'm going to read the problem carefully and fill in what I'm starting with as the 1s and what I'm ending with as the 2s. So what I'm starting with for pressure is 765 torr, and the starting temperature is 296 Kelvin. All right, the question is at what temperature will the pressure be 560 torr? So my new pressure is 560 torr, and my new temperature is question mark. Okay, so next I need to substitute. So my pressure is 765 torr over temperature of 296 Kelvin equals, my new pressure is 560 torr divided by T2. T2 is what we don't know. All right, to solve for this T2, when I have 2 fractions equaling each other, I like to go ahead and cross multiply. So I'm going to multiply the 560 by the 296 and the 765 by the T2 and set those equal to each other. Cross multiply, y'all. So 765 torr times T2 equals 296 Kelvin times 560 torr. That gets me closer to solving because T2 is no longer on the bottom. And the final step to get T2 by itself would be to divide both sides by 765 torr. 765 torr. 765 torr cancels out. The torr cancels out over here. And so I'm going to have T2 equals, it's going to equal 296 times 560 divided by 765. Okay, let's see if I can remember that from my calculator. 296 times 560 divided by 765. All right, we get 216.679. For sig figs, we want 3, so I'm going to say 217. So my final temperature, I'm going to write it over here in green. T2 equals, it was 217. And temperature is, of course, measured in Kelvin, so that is my unit. All right, does this answer make sense? The pressure went from 765 to 560. That's a decrease. And the temperature did the same thing. It decreased from 296 to 217. So the pressure decreased and the temperature decreased as well. So yes, this makes sense. Next up, number 3. A gas occupies 473 cubic centimeters, that's a volume, at 36 Celsius. Celsius. Let's get rid of that. 36 Celsius, let's add 273 to convert it to Kelvin. 309. All right, so we've got a starting volume and a starting temperature. Find its volume at 94 Celsius. Let's convert that to Kelvin. 94 plus 273. 367 Kelvin. That is my ending temperature. All right, so what is changing? Volume and temperature are the only things mentioned. So the equation to use, I'm going to do that down here. Remember, PV over NT. If volume and temperature are changing, forget about pressure, forget about number of moles, volume and temperature. So V1 over T1 equals V2 over T2. Okay, let's make our list. V1, T1, V2, T2, and reread the problem and plug in what we know. A gas occupies 473 cubic centimeters. 473 cubic centimeters is a volume at 309 Kelvin. Find its volume, so the new volume is the question mark, at 367 Kelvin. All right. Next step is substitution. We're going to plug those numbers in. So I have V1, 473 cubic centimeters, over T1, 309 Kelvin, equals V2, up here I don't know, divided by 367 Kelvin. All right, I'm going to show you a different way to solve this one. You could cross multiply. You could multiply V2 by 309 and set that equal to 473 times 367. That would work. But I'm going to show you a different way because V2 is almost by itself. So close. And it's on the top. So it's divided by 367. So I'm going to multiply both sides by 367. I'm going to multiply over here by 367 Kelvin. So what's left over here is just V2, those canceled. On the on the left-hand side, I've got 473 cubic centimeters times 367 Kelvin divided by 309 Kelvin. So you can just rely on the basic algebra rules as well. Kelvins cancel. So my volume, let's see, 473 times 367 divided by 309. I get 562. So V2 is 562. The volume unit will remain the same, cubic centimeters. All right, the temperature increased and so did the volume. The temperature went up and the volume went up because they are a direct relationship. Okay, two more. Number 4, a gas occupies 4.84 cubic centimeters at 71.8 kPas and 25 degrees Celsius. Ugh, 25 Celsius. We don't want Celsius, so we're going to do 25 plus 273, 298. Find its volume at standard temperature and pressure. All right. So we're going to remember, we talked about this earlier, STP, standard temperature and pressure, is 1 atm and 273 Kelvin. All right, so the pressure started at 71.8 kPa and it ended at 1 atm. So I'm going to switch to make the units match. I'm going to list my standard pressure as kPa, 101.3 kPa. That's an equal amount. Okay. So what is changing? Well, the pressure changed. Okay. Says it had a starting volume of 7.84, but it has an ending volume, so volume is changing. And temperature is changing as well. It started at 298 and it ended at 273. So temperature is changing as well. So all of these variables are changing. So in our PV over NT, the only one not changing is N. So P, V, and T are changing. So our equation will be P1, V1 over T1 equals P2, V2 over T2. Okay, we want to make a list of our variables. P1, V1, T1. I'm going to list them out. And then P2, V2, T2. Okay. So starting pressure was 71.8 kPa. Starting volume was 7.84 cubic centimeters. And starting temperature was 298 Kelvin. All right. Find its volume at standard temperature and pressure. So those are the new conditions. Standard pressure, I need to list it as kPa so that the units match. So standard pressure in kPa is 101.3. Volume, the new volume is our question mark. We don't know the new volume. And the ending temperature is standard temperature, 273 Kelvin. Okay. We are going to substitute our numbers in. So pressure, 71.8 kPa. Starting volume, 7.84 cubic centimeters. Ending temperature, or starting temperature, 298 Kelvin. Equals starting pressure, ending pressure, I'm saying the wrong thing. 101.3 kPa. Volume, we don't know. And temperature, 273 Kelvin. All right. For this one, we are going to try to get volume by itself because volume is multiplied by 101.3 kPa and it's divided by 273. We're going to do the opposite. I'm going to do the opposite, y'all, here in pink. Okay. So both sides are going to get multiplied by 273. So the 273 cancels. If it's divided by, you're going to multiply it. And then for the 101.3, because it's multiplied by V2, I'm going to divide by it. divide by 101.3. So over here on the bottom, I'm going to put that 101.3. You don't have to put the divided sign if you put it on the bottom. Divided by. Okay, so all that's left on the right-hand side is V2. So I'm going to kind of rewrite it all with just the numbers, not the units. So it's 71.8 times 7.84 times 273 divided by 298 and also divided by 101.3. You can just put it all in parentheses and not do the times sign down there. Okay, so let's grab our calculators. Try it out on your own and pause and see how you do. 71.8 times 7.84 and times 273 divided by 298 and 101.3. So look at the way I typed this in my calculator here. For numbers that are on the bottom, which we had 298 and 101.3 on the bottom there, you want to divide by them in your calculator. That's just like we did in dimensional analysis. And so my answer is 5.09. All right, so my ending volume is 5.09. The volume unit in use was cubic centimeters. All right, one more of the combined Gauss law. When an expandable balloon contains 2.5 moles of oxygen gas, it has a volume of 56 liters. What is the volume of the balloon if you add another 2 liters? Now, notice that it said you added some. It didn't just say it ended with 2. You added some. So let's think through what's changing. We're adding moles. Oh, no, we added liters. We added 2 liters. I think I have a typo here. It should say you added 2 moles. Okay, so we have a typo. Make sure you change that 2.0 liters to moles. So we are changing the number of moles, and we are also changing the volume because it says what is the volume. All right, so the equation to use if we think through PV over NT, get rid of pressure because it doesn't mention pressure changing, and get rid of temperature, doesn't mention temperature, just V over N. So my equation is V1 over N1 equals V2 over N2. So this is Avogadro's law. Okay, so the work that we do, we need to make our list, V1, N1, V2, N2. All right, let's go back and reread it. When an expandable balloon contains 2.5 moles of oxygen gas, that's my starting N value, 2.5 moles, it has a volume of 56 liters. All right, what is the volume of the balloon? So volume is question mark. If you add another 2 moles. So y'all, it started with 2.5 moles, and it says that we added another 2 moles. My final amount of moles then is 4.5. Why? Because that was the starting 2.5 plus we added 2 more. That's 4.5. Okay, we are ready to substitute. So V1 is 56 liters over N1 is 2.5 moles equals V2 is our question mark, and N2 is our 4.5 moles. Okay, to solve this one, I would get V2 by itself over here by multiplying by 4.5 on both sides. So times 4.5 and times 4.5. The 4.5 moles on the right-hand side will cancel. And so I have V2 equals, let's see, 4.5 times 56 divided by 2.5. Let's grab our calculator. 4.5 times 56 divided by 2.5. my new volume is going to be 100.8 liters. So V2 equals 100.8 liters. That is not the right number of sig figs, but it's kind of challenging to do 2 sig figs with a number like this, so we're just going to leave it as 100.8. All right, that is it. Thank you for watching. Key things to remember: if your variables are changing, anytime your variables like pressure, volume, temperature, and moles are changing, you are going to think about P1 V1 over N1 T1 equals P2 V2 over into T2, and you are going to get rid of the units that are not changing, keep the units that are changing, and that's the equation that will help you solve the problem. Thanks for watching. Hope this was helpful. See you next time.